Hello. So there is at least one problem, maybe two problems that I've realized that I introduced in the last video. So one thing is that we have this problem where we could have so so we're in kanji database.c. When we initialize the database, we sort by we sort we assign the radical stroke count keys to each character, and then in kanji distribution we use these where in places such as, oh, we're not using it in very many places. So the problem anyway could be that when we are when we're sorting things. So let's say we have these characters A, B, C, D, E. These are actually kanji. Imagine they are, and let's say this is a cutoff point. This is a cutoff point, and this is a cutoff point to this and this. And let's say this has rank 10, and this has rank 20, and this has rank 5, this is 30, and this, let's say this is 40. So the problem is that this character's rank is higher than this one. And so when we sort it in kanji.db.c right here, and we sort by the sort key, the radical stroke count, and then by the ranking, that means that suddenly C is going to pop up here, and A will be here. However, C is the correct cutoff point because C comes first in this in this hypothetical cluster. So in this cluster, they all have the same radical stroke count key, right? And so this is no good because really the first one in the grouping should have the cutoff point. Now there are a few ways to fix this. One is to stop using cutoff point bits and just store the radical stroke count key in database, and then populate the cutoff bit automatically. I feel like this is a little bit too extreme, and it's going to be a big change from what we have now. So I think that I'd rather avoid it because that could have more complication later. The other idea is to automatically reassign cutoff bits at initialization, and this is kind of messy and confusing for people that are reading it. So I think that even though this would require the least amount of work up front, I want to avoid it. And so what I want to do actually is I would like to have check kanji db order command verify correct ordering within a given rank. Okay, so in other words, it will make sure that the cutoff point comes first. It has the highest rank. So in a situation such as this, it should give an error. Okay, so now how are we going to do that? Kanji db order. Now I don't believe kanji db order does any sorting of the entire database. Sort and dedupe keys, sort info, sort key, sort info. Let's see, what does sort and dedupe keys do? Because I guess it does do some sorting of something, and it also does sorting in check order. So it does. Oh, it does sort by radical and stroke count here, and so here's probably where we'll fix the ordering, or we'll verify that the cutoff is correct. And so let me check out a different branch we'll go back up one commit where we kind of have everything sane, and we'll call this branch cutoff. Maybe set cuts for set cutoff. Okay, so now we're at this branch here, and we are going to use check order to make sure that these are that we have that we have the right cutoff bits. And I'm going to go ahead and have it report an error and then fix it manually because I'd rather just see what I'm fixing. And so I could like have it fix it in line and then reprint out the database information, but I have a feeling that it's not going to be that hard to fix manually anyway, and it might be kind of illuminating. So go ahead and do it manually, and if it gets to be boring, I'll finish it off screen. So so we're looping over every single character and in the database. And at this point, we should have access to cutoff points. So what we'll do is when we find a cutoff point, we'll set the rank of it. And as we go down, if we find any character that has a higher rank, which is not a cutoff point, then we report an error. So, excuse me. So how is a rank stored? Let's see, kanji db.c, kanji db.h. So we store rank as a uint16 type. So it may be nice to actually use like a type def to say that it's a rank type. I don't know. Maybe that's a bit excessive. uint16 type. All right. Let's just try it. Rank T. Okay. So we have rank T cutoff rank, and if this is this file is changed. Let me reload it. Okay, cutoff rank. Now the very first character should be a cutoff, and so it doesn't matter what we initialize this to, because the very first character will be setting it. So let's see, if ki dash we call it cutoff type, then we got to set cutoff rank equals ki dash ranking. And what else do we have to set? Do we have to set anything? Maybe we don't need to. So I'll just say else else if, I guess, k ranking is less than cutoff rank, then this is an error. And we can say we have this here. We have break. Maybe we'll just do the same thing. We'll say xf printf. We'll call it kugi giri. And we use the string. And we call it ki dash c. Right? We print out the character and we say that there's an error, and we break. But at the same time, maybe we don't have to say this is a fatal error, because we can keep on going. kugiri error equals 0, and then we don't have to stop. So just say kugiri error equals 1. All right. So if kugiri error, then res equals and not res yet, then we say res equals 32. So if there's no error calculated yet, then we set it to 32 and we return at that point. All right. So now we can probably make it and see some failures. Check kanji database order test. Exit 32. Oh, but we didn't actually print out the problem character. That was dumb. Because otherwise, maybe we can store an array of the cutoff errors. So we'll say we need an array of characters that have cutoff problems. So I'll do struct kanji entry. Do we have any kanji entry array type? Let's see here. Struct kanji entry array. Maybe we just want to make this into, put this over here. Array. So we'll do a struct kanji entry. It's double pointer L and size T count and size T alloc. Now, what is this? How is this going to be a const? So we don't need the element itself to be a const. When we dereference it, we want to have a constant. We don't want to have a constant there, but when we fully dereference it, we have a constant kanji entry because we don't want to change the database itself. Okay, struct kanji entry array. So cutoff. So kugiri errors equals there. So down here, we'll say that we no longer need this flag here because we have an array to read from. So if, or let's say, grow array by kugiri errors 1, then we say kugiri errors dot l kugiri errors dot count -1 equals ki. Right. Okay, and down here we'll actually check them. So if kugiri errors dot count and not res, then res equals there, and then we have to print them out. So if kugiri, how are we going to print them out? Oh, let's just use this here. We'll reuse our if to create a scope. Size T error I, and then let's not forget to destroy the array. Errors, okay. And let's see, so I'm almost out of time. If not res, okay, put it here. So, error I. Now we can start looping over it for error I equals 0, error I is less than kugiri errors dot count, error I plus plus. Okay, and then we just print it out. Let's let's print it all out like this. Standard error kugiri error. Okay. XF printf. Really, I should just be putting a string, I guess, not using a printf function, but I haven't really been doing that lately. I'll just keep it like this. It's nice to like have a limited number of functions to know about. So rather than make an xf put s, I probably already have an xf put s, don't I? Xf open get s. No, I have a get s, but not an xf put s. Man, f put s here. So I could just use this f put s. I don't like the way the stream is later, is the second argument, but it's consistent with put c, I guess, but it's not consistent with the printf thing. Yeah, what should I do about that? Void xf put s and char const s and file stream. Let's put that after xf get s at util.c xf get s down here. So then we do int res equals f put s, and oh, are we going to return like the length or something? Return value put s, return a non-negative number on success, so it's not actually an informative number. End of file on error. Non-negative number on success. Okay. So I'm not sure if we should pass on the return value. Maybe not, because it doesn't sound like it's potentially interesting, since it's not defined what it actually is. So I'll just continue to return void. If res equals EOF, then we say f printf standard error f put s error. Or maybe we should do this. We should do like f put s excuse me. All right. We have to order the arguments correctly. Standard error, f put s standard error, and then exit, and we'll have a random number, random.org. Generate 155. Okay. And then we just return. Okay. If res is less than 0, then we have a bug. Because according to this, it will either return EOF or non-negative number. So if it's a negative number, then we can say bug unexpected return from f put s. Okay. So here, let's change this now. Xf put s. Xf put c. Down here, we'll do xf put c for the line break. All right, and here we do xf print f, or xf put s, I guess, and we print the actual character, cookie errors.l error I dash c into standard error. Okay, and this is definitely going to find some problems. Compile errors, cookie errors. Oh, mistyped that. Kuguri. That's not correct. Kugiri. Okay. All right. Oh, wow. There's a lot. That doesn't seem right. There's no way that there's that many. If there are that many, then we're going to have to fix it automatically. Edit kanji database.c. Let's just pick one at random. See if that seems right. So go. Oh, but the thing is, it's going to report it for every single character. So here it reported it had to report it 4 times, which is not that great. We should have just reported it once because we only have one line to fix, right? So here, let's fix this one. And let me just visually check that that's the correct number of stroke counts. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, that seems right to me. 1, 2, 3, 4, 5 there. And then 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. Okay, good. And let's just fix this one while we're at it. Now we'll probably see less, but not a lot less. Okay. So, yeah, maybe we have to do this automatically because that's a lot. Let's do kanji database.c. Let's check kanji database order. Okay. So what we'll do is we'll just print out one kugiri errors.count. Okay. Cutoff rank. If cutoff rank. So if cutoff rank is 0, that means we don't actually use 0. So kanji database.c, we probably should not 0 dash. I think we don't use 0 as a rank. No. Cutoff ranking. Otherwise, if that is an n, so here. That means we only report it once for each problem. Okay, so this is still quite a lot, but it actually is more honest about how many problems we have. And so I'm gonna have to do this automatically, and let me take a break. But for now, we've kind of gotten we did get something done. We got like this code which finds the Kugiri problems in check kanji database order. I guess what we'll need to do is we'll need to have this fix the errors automatically. Thing is kanji database order. So kanji database. So So the thing is, kanji database.c only gives a read-only view of its database. And so what we might want to do is have the logic to fix it inside of kanji database. Oh, actually, it doesn't return a const here. It does not. That's interesting. Okay, let me think about this a little bit, and then I'll continue. Okay, so I have an idea about how I want to proceed now, having thought about it for a while, several minutes. But it's a little complex to explain. And before I do that, I think I'd like to make a few less ambitious changes. So I am going to change gears a little bit. A lot of what we already did is still useful, but what I want to do instead right now is I'm going to fix where I've used the word rad SO for meaning rad stroke count. because it actually should be SC to be correct. So it would have to be rad SC, and so this is kind of a less ambitious change. Maybe, but I do have to type it a lot, so maybe I'll just call it RSC, radical and stroke count. And so we'll look for radso in the code base, and I see all these. Let's check for some alternate spellings like rad.so, and count the number of instances we have of that, because this basically means it's a wildcard. So we'll do rad-so as well. That will find everything, and then we do rad_so, and that's also 24. Okay, so all uses are apparently using the underscore to separate it. Now, I wonder, does this include the parent directory? I guess no. Grep rad so. Okay, so there's one extra occurrence if we're outside this directory. So we have where is it? Check kanji db order, which is some kind of a script, and dump rad so. Okay, so some of these scripts are probably not needed anymore, like dump. Let's see. So let's put something on the agenda here. We're rename rad so to radsc. Okay. Now let's open up new sort / check kanji db order. Okay. This is an ancient script I wrote, which does the same thing as a radso check kanji database order thing. So let's also look for dump. Let's look at the dump radso, which is the other match we have. And okay, so here are the the manually entered keys, which we use in addition to the Unicode given radical stroke count keys. And this does the same thing as check kanji db order command. So so let's go ahead and get rid of it. We'll go to git branch and start it at we'll call it cleanup or radso or radsc, and then let's do rsc, and we started at h5, right? So rsc. Okay. So let's see here. What other scripts? Check kanji db order. So we also have these files, which are probably not needed anymore. Less top 1241. So this takes the top 1,241 characters and sorts them by radical and stroke count order. But let's just remove the things that I'm sure we don't need anymore, which is check kanji db order and dump radso. And so we'll make a commit, and this will be delete scripts which have C implementations. Fuller C implementations. Okay. Good. Now next let's look for files that have that radso name in them. Grep rad.so. Looks like we have these 4 files. Okay, so let's fix that. Move to rad rsc sort. Numbered. Then without the numbered, right? And git move top 1514 radso sort to top 1514 rsc sort. Okay, I'm fast forwarding a little bit because I was just distracted a whole lot while I was doing this renaming work, and so I am not record. I'm left out the recording of me finishing this up. So, um, so there's something else I wanted to do. I would like to, I think, change this to a const and see if this still works, because really, no one should be changing the kanji database content outside of the kanji database module itself. So let's just see if this still builds. Um, so no, it's not building correctly anymore. Let's open kanji database.c because we didn't actually define the function properly. Okay. No. Discards const qualifier from pointer target type. Okay. So in my macro here, I assume that the array that I'm getting is not is like of non-const elements, I suppose. Here. Oh, okay. No, so actually the macro itself is fine, but when I use it, I'm assigning a non-const pointer to a const pointer. Because right here, E is a identifier supplied by the caller of the macro, and apparently was not. If I understand right, it was just not declared as const like it should have been. So let's see, we're got to go to line 60, right? This should be const. Well, let's try again. Good. Okay, let's commit that. Make kanji database function turn a const pointer. Okay. Now the other thing is that we've been having problems with the way our new sorting scheme works. So let's go to my notes page. So what is the problem here? The problem is that we are trying to sort characters according to their radical stroke count keys, which are now no longer unique for every character, but some characters might share the radical stroke count key. So that is a problem, because now a lot of characters like these can all be sorted in an arbitrary order, a kind of unpredictable order if they all have the same radical stroke count key, because the way I wrote quicksort, it's not going to be a stable sort. Now, the way I tried to handle that was that we, rather than try and make the sort stable where it like keeps equal keys in the same order, I at least try and make it somewhat predictable by sorting by the radical. And that is apparently not working all that well, because if we sort by, sorry, did I say sort by radical? I meant sort by the ranking. Now that is not working very well, because that ends up putting characters in strange orders. Like it puts the cutoff character in the middle of the cluster of kanji sharing the same key, and we don't want that. And so the way we can solve this is by actually forcing the sort scheme to continue to sort in this order of like the radical stroke count. In other words, continue to sort in the exact order that we have right here, that we type explicitly into the kanji database. So if we look at where we are in the commits, so we're in this tree, we're no longer at this where the commit we're changing the sort key. We no longer have these changes, and so in this state of the repository, you can see that we're assigning rad stroke count sort key equal to whatever the index of this is. And I thought about ways to fix this, but all of them are going to require some work to kind of keep the results the same. And so what I think I would like to do is to just use we're going to change this so that we never sort this array, right? So we always keep them in this order. But when we need it in a separate order, like right here, apparently we need it in a separate order right here, we will instead sort an array of pointers to it. Okay, so we're going to instead sort the array of pointers, and then when we actually do compare to radical stroke count key, when you use that key to compare and the key happens to be equal, then we're no longer going to fall back to the sort by ranking, which is causing problems. Instead, we're going to sort by whether or not the key is a cutoff point first, and then if it even still is a cutoff, if it's still the same, then we're going to sort by the value of the pointer. Okay, and that will finally get us to remain in this like order that we put it in the database. Now, first of all, before you even do that, I want to make sure that we need this sort here, because maybe we don't even need this sort exactly. Maybe we can just rely on the caller to do the sorting themselves. So this is sorting by the Unicode code point, and I'm kind of thinking that maybe it does need to be in that order. So let's see here. Yeah, I'm thinking that it does need to be in this order, and if I try and change it, it's going to just, things are going to break. Yeah, something failed. Last rank contained test failed. And so this thinks that this can't find this character in the kanji array. So it's which is dumb, because apparently this is using, it got confused. It was not in the sort order that the binary search expected it to be in, and it's really hard to search for. So the thing is, we want to be able to search for this without having the actual kanji. Only having the kanji itself available and not having the kanji entry pointer. So there's two aspects to the kanji. It's the actual code point, which is right here, and then there's the other data like the ranking and whether or not it's a cutoff point. And that block of data is like kind of a singleton for that kanji, and there's only one of them. And so if we don't have the pointer to this block of data, then we probably only have this character here, and so that's why we were sorting it in this location. So we're gonna have to keep that there. Now we actually are gonna have something like an extra array, like we're gonna have a kanji entry E, or sorted by code point here, and then we're going to populate this down here, and we're going to keep this in the same order, right? And then when we actually sort by the radical stroke count, we'll sort by the pointer, because the pointer will be in this order, obviously, because that's the order that this array is because we're going to be using pointers into this array. So we're going to store the sorted by code point thing separately. Okay, and so kanji database. Now maybe we don't even need to expose this kanji database thing. I'm wondering if we want to expose what we want to expose to callers. Do we want to expose this array itself? I'm thinking maybe we only need to expose one ordering for the kanji, and that is with this one. Or maybe we don't even want to expose this array at all. But no, I think we need to, because there are callers that need to get every single kanji. Okay, so all right. So what do we need? What can we keep here? We have so this is where we're storing a few tests in a separate file. Let's pull this. Let's grab this out. And what did we do for number 5 here? This is, okay, this I think we're not going to need anymore. This is where we are trying to figure out where all the problem cutoff characters are. But we're going to be sorting to avoid that anyway, so we don't really need this. But we do fix something here. We actually fix these characters so that the cutoff point is with the highest rank kanji, which I kind of like that scheme. So I'm going to pull that file out of here, out of this commit, and then the rest of the commit I'll just drop it. All right, so let's go to set cuts branch, and then I'll rebase it onto pending. Okay. And so now we're going to check out pending and put it onto set cuts. I don't think we need to separate the branches anymore. And now we delete set cuts, right? And here we want to split up this commit, so it includes this file as a separate entity right here. So we can probably accomplish that. Oh, I also like this fputS function. I kind of want to keep that as well. Okay, so how do I actually split a commit up so that it only has certain files in it? I think I've forgotten how to do that. Let's see here. Git rebase. Yeah, I think we want to do rebase. Git. Okay, it looks like the answer to my question, based on a quick Google search, was to just do git reset --soft head ~1, and this will get rid of the commit that you currently have. See, now we have one less commit. We're on stashing radso sorting key change, and before we were on just on the one after it. We were on this one. So it's this command, git reset soft head ~1. Now, so I want to have util, so util.star. This has the xfputS function, and I will save this here. xfputS function. Okay. And I'll actually move that around to a different branch later on. Oh no. I committed everything instead of just what I wanted. Okay. Now I already changed my mind. So let's just do this. Let's just store this fix right here. Right? We'll say, what file is that actually? That is that all in kanji-db.c? Yeah, it is. There's nothing else in kanji-db.c. So we'll do kanji-db.c and call this more cutoff fixes. And now kanji-db.h. We can just trash this. We don't really need this. Check out kanji-db.h. How do I actually unstage it? I think it's git reset. Check out kanji-db.h. And the other one is this one. We are not going to need this. So I will just get rid of this. Git reset. Check gdborder.c. Alright, now I'm going to change the rest to put it on master, and I will commit xfputS function. Alright. Check out -b xfputS, put it on that branch. Okay. So this will save later, until later, when we actually have an opportunity to use it, which will be soon, because I'm always writing printf statements without any formatters. And then this is good. This cleanup is good, and this rename is good. And this deleting extra scripts thing is good, or deleting obsolete scripts. So we'll go to pending and rebase onto the cleanup stuff. Uh-oh. So we had a conflict when we were doing what? Conflict in kanji distribution. So this is when we are applying this radso sorting key change, and this is probably because we are using a field with an old name. So let's go to check kanji order.c, and here merge common ancestors. Okay. Right, rename the key here. So here we're going to call it, alright. Is that the only merge? Yeah, only conflict. Check kanji order.c. Alright, now kanji db.c. Okay. So we don't need this. We can just keep our new change right here. But radso sort key is going to be sc now. And this c. Alright. sc. Show count sort key. Alright. Radso. Alright, then we'll just change this radso to rsc. Okay. That's then. Alright. Now this is fine. And now we gotta fix the header file. .h. Radso sort key. Okay. So the difference is that this is now a fix with type uint16 type. Right. And the problem here is that it should be const. Kanji entry. Huh, I don't know why there's a conflict here. It looks like I didn't. Oh, because I added a new function under it. Okay. Okay. Kanji db.h and kanji distribution.c. Alright. That's the only one, okay. Now we can try and make sure that it builds. No, it doesn't build. Kanji db, I didn't use the right name. Here. There, alright. Okay, that builds. It doesn't fail the test because we already updated the test with the incorrect output that is that we need to fix today. So now we got to do git rebase dash cast continue. Base. All right. Now this more cutoff fixes thing. This needs to go down a little bit. Git rebase dash I. 9. Cutoff. So good. Alright. This is a fix up of the other cutoff fixes commit. Now if we go down to number 2, we want to make sure the tests pass. Good. Okay. Now let's go back up to pending. Now kanji db, this is going to return the kanji in the code point order. And but it would probably be nicer if so this is going to now return a pointer to pointers because this is no longer giving the original pointer, the original array itself. It's giving an array of pointers which have been resorted. So we're going to have to change the API to be like this, but that could be that could make the CL kind of big. So let me or the commit rather a little big. So we'll go back to number 2 and check out a new one for pointer type. Right. So it's going to do this. Okay. Pointer type. Let's see. Let's open kanji-db.c and we're going to change this. Gives the kanji database in you know what? This is awkward, this NR thing, because we could just have it as an array. So we'll be like kanji entry array, right? And we have a struct kanji entry. Oh, let's just call it kanji array. There. Kanji entry const elements, and we'll use the naming convention that we use for the other for all the other array types, size t count and size t alloc, right? And kanji-db in Unicode code point order. And this is nice because it's kind of in the same it uses the same convention as like the usual well, it uses the same convention as all the other arrays that we use. So we'll change this to a return a kanji array. Struct kanji array const. So maybe this should not be const because it's returning a const here. So this is this is getting kind of weird. Because we want this to be const. We don't want them to change the entries in here, and we also don't want them to change this entry here. But those are two different const keywords. So we don't want them to change this entry, but I also don't want to have to make this const because I want to reuse this array thing. So maybe we don't really want to use this like array approach, right? Because we're not going to be able to reuse it for anything anyway. Alright, so returns kanji entries in code point order. Alright. Okay. Now we have a static struct kanji entry const code point ordered database. Oh, and here we have sorted. We don't need this anymore. Do if not code point ordered database, then we allocate it. Code point ordered database equals xcalloc. What is the exact function we like to use? xcalloc count and size. Okay. So count is kanji dbnr, and size is size of kanji. Let's just call it kanji code point ordered, not with the db on it. We don't need that db. Code point ordered. Alright. So then we're going to copy it to code point ordered I equals, oh, so we do want to set the stroke count, the RSC sort key here. But wait a second, I thought we already had that. No, we didn't. Yeah, this is before this commit. I forgot that it was before we did any of the changing of the way we store the keys. So this is, yeah, this is a little different from what I thought. So code point ordered. Now we set code point ordered. I is equal to kanji db, or we call it just kanji I. Right? And the sort key is set here to I. And here we actually sort it by code point ordered, right? We sort the code point ordered array there. And here we return code point ordered. All right, let me just reread this again. So we're allocating it here. And we iterate over the number of elements. Code point orders I equals address of kanji. And so that's populating it. All right, here we use the right dereferencing method, and this has to be code point ordered. Point ordered. Okay, now I have to wrap it, I guess. That didn't work. Just do a static int code point less than, and we'll have a separate function for this. Struct kanji entry const A and struct kanji entry const B. And this one has to be wrapped too. Okay. Then we return strcomp a-c and b-c is less than 0. All right. Change this to code point less than. All right. All right, we don't need this anymore. Okay. This looks fine. We don't need the C. Don't need to dereference it like that. But now I feel like we don't really need this anymore. So we can just do strcomp here and C. Right. And we'll just do less than 0. Okay. Great. Now, all right, let's try and make it. We're obviously going to get a ton of errors because of the callers of kanji db. Code point order db, we don't need the db. Sorted equals 1, don't need that. And more errors. It's repeating errors, that's bad. I really need to debug the make file. Kanji db I plus 1. Alright, kanji db order. Check kanji db order. Alright, edit, check kanji db order. This is 250. Right, so here we're copying. Okay. Yes, that should be all you need to do. L121. No. Kanji distribution. Line 60. Kanji DB string comp. Cutoff. Okay. With. Okay, cutoff. It's gonna have to be this. We are gonna have to dereference it accordingly. Off. Not sure why I didn't wrap the line like that. I'll just keep it the way it is. All right. Let's try again. Cut off line 64. Return. Cut off. Because cutoff is pointing to a certain place in the array, and that's why it's kind of awkward. It's pointing to a pointer to a kanji entry, because it's pointing to a place in the array. So we dereference it, and then we get a kanji entry itself. Yeah, that seems right. Okay. Right, I think we're getting closer. And distribution 64. Return from illogical pointer type. Construct. Static. Y. 138. Oh, because I didn't save it, I guess? Alright, good. So here. E. So let's make this a, let's order the const properly. Struct const E equals kanji database I. Right. Grow array by resorted. E. Okay. Util.h. Gotta go to kanji distribution, line 204, cut off. Cut off. Right. Same deal as before. Cut off. All right. Good. Good. Okay. So now we can go ahead and say that we're done with this. Do not sort original copy of kanji DB array. We want to use the pointers for use in comparison. All right. Now the alternative would be to go ahead and sort the original array, but then just have an extra field which indicated where was this item in the original array before we sorted it. But that just seems a little confusing. It seems like roundabout to me, and I don't really like the idea of sorting this array anyway. I'd rather just keep it in place. No. I mean, considering that it is like a static piece of data that's initialized with a bunch of constants, just resorting the whole thing seems surprising. Stashing Radso Circuit change, okay. So now we can probably go to pending and rebase it onto p pointer type. All right. Now we're going to have a few conflicts naturally. Okay. So the new thing that we're doing is that we have a sort key separately, which we're incrementing separate from I. And we are setting the, so this is the one we just worked on, right? So here we want to go ahead and say that, well, we want to use what we have here. If it's a cutoff type, then we increment the sort key, and we set the sort key of the kanji to that value rather than to I. Or right? And then we sort based on code point still. That's fine. At kanjidb.h merge common address. Okay. Const. Common ancestors. Okay. All right. Now if we make, okay, git rebase, continue. Good. Now we actually want to fix what we did before, kanjidb.c, where we're sorting it by the radical and stroke count. Now we want to sort it by the sort count key, but if that's the same, we want to sort it by the cutoff point. Cutoff type is not equal to b dash cutoff type. Then return a dash cutoff type is greater than b dash cutoff type. All right. Now, if those are also the same. Well, the thing is, we don't have to check the cutoff type because we always put the cutoff one in first in the original array. So really, this is kind of redundant. I'm pretty sure this is redundant. Let's say that we just do if. So here we're going to just return a is greater than b. Right. Okay, now we're going to see how tests probably go back to normal at this point. Okay, lots of differences here. This is the typical Kokiri kanji test.test out. So why did it change so much? Let me see if we changed it a whole lot here. Yeah, because we changed it here. Last rank contained test Kokiri kanji test. So I bet this is actually going. Now we're probably going to go ahead and bring it back to what it was before once we apply this diff. Right. CP. All right. And make string contain test. Okay, the next one that's different is Kokiri kanji with showing count test. So yeah, this is expected to be totally different because this is the same as the last one, but it just has an extra number at the end. So copy. Oops, that was not right. Oh boy, I guess I'll change this to a separate window so I can see it better. Let's try again. All right, this is easier. Do a copy. All right. Now just one thing is different. Error, exit. Something has an error. Check kanji database order, test quiet. Now, why would this have an error? This looks like the character that's in the... Yeah, I think I recognize this. So, okay. Interesting. I wonder what that error is. Let's look for that character. Here. Could it be that we're not using the right rank character here? I don't think so. Let's open check kanji database order. So, hold on. Let me just check our little sorting thing here. Oh, you know what? I think I know what's going on. Go to check kanji database order. I think we're maybe not sorting this properly. We're sorting it. Check kanji database order. Q sort. Sort infos. No, maybe this is not wrong. Okay. Oh, here. Q sort. Sorting it by this. Sorting it by essentially the order that it is when we have it there. Okay. Same order as when it's in the database itself. Kanji DB NR. Be them. Then it's copying everything into here, and I don't see why this would be a problem. So we have this xf printf here. This means that according to the radical stroke count key we found in the Unicode data, it does not match. The characters were in the wrong order in here. So that's interesting, and I don't understand why the problem is found now but not earlier. See if I can count the strokes here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 residual strokes. Now here it is 6, 7, 8, 9, 10, 11, 12, 13, 14. I see 14. Okay, so 12, and then the one in between here is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So I guess these should all be cutoff characters. And this one is, I'm not totally, I don't want to spend too much time counting. Kanji, here we go. So this one has 1, 2, 3, 4. This one has 15 residual strokes. And this one I think had 14. Yeah. So this needs to be, and then this has 13. Yes. And this should have 12. No, this is the same. So 12 and 12. No, minus 4. This is 13. Yeah, this is 13. This is also 13. So maybe there's a confusion because there's an alternate writing for this which has an extra stroke right here. So apparently these two are the same, but this one has one more, and that might be why it's not working. But I don't want to just change this without really observing what's going on. So now did we... Yeah, let's... That is kind of surprising. 1. So what did we change in kanji database order. Check kanji database order. Sort by sort key. But now we don't do that anymore. Stroke less than. Are we not calculating the sort key properly in kanji DB? Code point ordered I, kanji I, raster sort key. Cutoff type. If it's cutoff type, then we increment the sort key. And here we use the sort key to decide which goes first. And oh, this seems wrong. This ought to be less than here. Okay, now this is probably going to be different again because we didn't use the right. We didn't actually. The last time we were doing the opposite of what we should have been doing. Inside of the same group of characters sharing the same radical stroke count, we were sorting according to the opposite of what we were supposed to sort. They're sorting them backwards. So that would explain a lot. So let's go ahead and fix this here. I'll do the same thing again. Copy this to this. Okay, then make and copy this, and make. Okay, good. Now let's amend the changes and see how much the CL actually changed. Okay, good. It didn't change nearly it didn't really change that many tests this time, which is basically what we wanted. We didn't want to change we didn't want to have to reevaluate so much stuff. Automatically find, it's better not have to evaluate too much in one commit. Automatically find cutoff characters. So this is different. Can't really say exactly why. So sorting by the stroke count key, and then it's sorting by, then it's sorting by the pointer itself. I assume that if we sort by the pointer itself only, then it will give exactly the same results. But no, that doesn't make any sense. Oh, I remember now. I was looking at this code earlier. We're not actually using the sort. I think it's because we're not using the sort properly. Last rank contained. We're in qsort. We're doing something kind of dumb. Last rank contained. Not qsort. Pattern not found qsort. That's surprising. Alright, we have to go to edit kanji distribution. Qsort. See, when we end the line, we're sorting it by the stroke count, and that's okay, that's fine. Here, sorting by ranking. Here we're sorting by the sort key. Auto pick cutoff. Yeah, I think this is not how we want. We don't want to sort by the sort key, because then we're not going to find the right cutoff points, because this does not cause the cutoff characters to appear first in the group. And each cutoff character has to appear first in its cluster of shared keys. So this is going to have to change to RS radical stroke count less than, and we do this. So that. Okay. Now Check kanji database order test quiet. Great. Now we have a fail. What? Why would we have a failure? I thought it was just passing. Oh, this is make map tests. So never mind. Okay. All right. Let's go back here to our big window and default mapping test out. Let's fix this. Yeah, this is probably going to restore everything to what it was before we started the refactor. And here, more. Okay, good. Now, why is there still changes in the test? I didn't expect that to happen. Wait. Seems like there are no change. Ah, yeah, okay. There weren't any changes. I was using the wrong command to look at the current commit. Okay. Good. So now there are no longer any changes in the test. So I think what we'll find now is that we're not actually using this sort key value anymore. But we do want to use it for we're going to use this to help make the output of last rank contained a little more readable. So I bet we can just get rid of all uses of this and it would still, the test would still like pass, because we're not using it anymore. The only time we use it is in this comparator. But we can just replace this comparator with this less than check, and that would still do the same thing. So I guess that's what we should do. We should just get rid of this, right? That would make, and get rid of, maybe even get rid of this. At least for this commit, we don't need this anymore, right? But we're going to add it back later. We're going to add it back when we actually need it. No, well, maybe we can actually start using it in this commit, because I don't want to have to go and delete stuff and then add it back right again later. So let's go to let's go back into our development window. We're going to go to kanji DB, and we're going to change this to just do that comparison, and everything should still pass. Good. Okay, so we don't need this. So git grep rsclt, check kanji. Alright, let's get rid of it. Check kanji DB order 252. Okay. Okay, let's make sure that works. No. Oh, because I deleted the actual declaration of it, so I can't do it. I can't do a single check. I can't do a gradual change. I have to fix everything. Okay, git. So grep s iron rs. All right, edit kanji distribution 130. Okay, here. Qsort. See, now line set 170, we have this. Okay. Good. Now I think that this is going to look extremely simple now. If we look at this commit. Yeah. We're just using the pointers rather than the key. So now let's actually add like a method for seeing the results of this. Last rank contain.c. Now we're going to add a flag. Let's add a documentation for it in main, and last rank contain has a. Now we'll take a a C flag, which shows the cutoff points, shows the cutoff points inside of the actual lines, if there are any, which there usually will be. Inside each line, it will show the cutoff point. Okay. Save that. And let me just think here. I don't like the formatting very much in the code, but that's probably fine. Not a big deal. Static constant char usage. Okay. So now let's go to last rank contained. We're going to add C, and this will be this will be local to this command. It's not going to be used by kanji distribution itself. So show space for cutoff points. Show space for cutoff points. And are we actually resetting this stuff to 0? Show per line kanji count. Shows hide kanji. Oh, this is kind of weird. So we're forgetting to actually reset the flags, which is bad. So let's do this. Unsigned. If we allow you to memset the struct, it's going to be harder to forget to fix it. So flags.hidekanji and flags.show per line and flags.show space for cutoff points. So you have those three flags. Unsigned. Show space for cutoff points. Right. Okay, and then we don't need this thing anymore, but we do need a memset. Address flag 0, size of flags. Okay. Good. Good. Show space for cutoff points. Now we have to go here, and we are xf printf xf printf. Okay, here we can actually use that that xf putf function for in a nice way. But we also have to print a space if we need it. So we'll call this edit util.h. We have xf put s. Do we have xf put c? Not xf put s. Okay. Okay, now we're gonna add. Let's delete that old branch pointer type. Don't need that. And now we're going to go ahead and source copy. We're going to amend this, and we're going to cherry pick this xf put s function, and we're going to delete xf put s. Right. And now we're going to merge these last two commits, because we're going to use it here. Okay. Now, xf put c and xf put s dash e I dash c. Right. Into out. But we also want to see if we need to put a space here. So if if s dash, if we're not at 0 and s e I minus 1 dot rsc sort key is not equal to s dash e I dot dash rsc sort key, then we got to print a space. Xf put c All right. Okay. Yeah, the formatting is unfortunate here. Okay. Hide kanji. So, but here we also want to check the flag. If flags.show space for cutoff points and I and here, let's see. Ah, good. Maybe we don't have to do this wrapping, the awkward wrapping that I was doing at first. I and okay. Put S. Yes. No, we do have to do the wrapping. Darn. Unless we cheat and undo that spacing. Alright, show per line kanji count. This is flags. Okay, good. So now we can actually do a last rank contained -C for cutoffs. And okay, this is going to group together characters that have the same radical and residual stroke count. And it looks like there's quite it's actually kind of rare for two characters to have the same radical and stroke count in this like selection, in this selection of 1250 characters. I really don't see that many sharing. Like here's it's sharing, and here it's sharing, and here it's sharing. I bet it's sharing in the hand radical quite a lot. That should be right. Where is it? No, maybe not. I don't see a lot of sharing here. Here are all the hand radicals. Oh, there aren't that many. There's like a certain key where it's like the hand radical plus 4 or 5 residual stroke counts, where there's a lot of just characters that have that exact pattern, which is hand radical and 5 or 6 residual strokes. But I do see, some interesting stuff. Like these all have the same key. These have the same key. That's kind of interesting. Okay. Anyway, so now I want to test for what we just did, even though it's not really super useful, but it's still not that bad either. Except print. Yeah. Okay. So let's write a test. Edit last rank contain test. And this is automatically find Kugiri showing space for cutoff. Potential cutoff. Let's not do that much detail. Just showing space for potential cutoff. And it is with -C flag. And we use a separate file to store the output. Okay. Okay, cutoff. So I want to create that file for output. And we're going to copy the output into the actual file. Okay, good. So this was quite a session here. But we're just about finished. flag show per line kanji count. So printf. Okay. So we can just do this amend, and I will edit. How do I edit? Git commit dash dash amend. Yes, dashing. So store non-distinct RSC sort key value. This allows us to have a -c flag in last rank contained that makes the change of RSC sort key between characters easier to see. Okay. Good. So what do we do today? So these are like the changes that we did separately. So these two changes I think can be pushed without any further alteration, and I don't have to talk about them again. But maybe I do because they are because I wrote some English comments that I want to translate. So C4, C3. Okay. No, I guess not. I don't see anything that I have to fix in those. Git rebase. Let's put those first. All right. Oh, what happened? I left this extra reference behind. That can be deleted. We delete scripts. And, all right. So let's run the test for everything. All right. 7 is fine. 6 is fine. 5, 4, 3, 2, 1. Okay, good. So all the tests pass. Pending. And okay, so what did we do? So we already talked about this in the last video, but for this video, we delete the scripts which were ancient, which now have C command equivalents for them, and that is that. That was simple. Next, we renamed the radso identifiers to be RSC for radical stroke count, and to make that a little bit shorter, which kind of makes sense since it's so commonly used. So we go ahead and use a shorter name for that. And so that fixes the name. And then if we go to C3, we change the way pointers are handled here. So we return a const pointer, a pointer to a const rather than just the writable data. Right? So now we go here, and here we change that even a little bit more. We no longer return the original copy of the kanji database. We return a resorted separate copy, which only has the pointers into the original array. And this is a little bit cleaner because we need to use the pointers of the original array as sorting keys, right? So that's fine. And here, store non-distinct RSC sort key value. Yeah, so this is like new functionality. This gives us a flag. This we store the actual like real radical stroke count key. We don't store some proxy, which is just the index into the original array. Now, on second thought, you know, I did actually like here we keep a copy of the kanji DB array, But that's less efficient, I suppose, than storing a like here, kanji_db.h. So we could just add a new key here, which is the, you know, the monotonically increasing value here. This is like the old radso sort key, which is different for every character. And technically, this would take up less space in memory than storing an extra sorted copy of the kanji database. And so, maybe I do want to do it that way instead, because I'm not so sure about storing an extra sorted copy if it's less efficient. I mean, I guess I don't care about efficiency that much. But the thing is, I don't want to change something if I'm not really getting anything better out of it. I think before I wanted to sort a new copy of it because I guess I didn't like to write the array, right? I didn't like to write that statically allocated array and cook up the data before returning it to the user. But I don't know if that's bad. Maybe it's good to avoid that. Maybe I don't actually want to sort that array. Let me think. The new sort source. So I mean, it would not be that hard. Like, I guess we need to backtrack on this commit, number 2. We kind of don't want to do this anymore, I suppose. We, yeah, we would back out of this commit, essentially. And then how much work would we have to do? We're going to have to, like, merge these changes again. So I don't want to have to merge any changes. I don't want to put that much time into this, because essentially we'd have to get rid of this commit, and then this would have to be redone, because this changed again in the commit after it. I don't want to have to change it again. I don't want to have to merge it, I mean. Well, what I could do is just merge these 2 commits and then kind of undo the stuff that's not necessary, I suppose. Yeah, I don't know. Well, I'm not feeling decisive enough to do anything right now about it. So I think it's good enough to just say that we're done for now, and so I'll stop the video. This is probably a decent enough point to cut it off, and I'll think about whether or not I want to revert this just off screen. I'll think about it. So thank you for watching. Okay, I wanted to end the video, but I also wanted to really fix this, because I'm starting to dislike the fact that I have 2 copies of the like 2 different independent arrays or 2 different orderings in memory in the kanji_db module, and I didn't like the fact that I was doing less than, like a raw less than, without any kind of without a real good reason why. So in other words, this stuff right here, where did I do it? RSC sort key. No, maybe it's in check kanji_db order. Where is it? So anyway, there was a place where I was using less than to just compare the pointers of kanji entries, and that's just it's just a confusing thing to have to understand. So I think I did it in qsort. So qsort star less. Sorry, like here. in kanji distribution.c line 130. 130. So this is just kind of weird, and it's surprising that it works. So what I'm going to do is I'm going to backpedal, and I'm just going to merge these two changes and undo the stuff out of number 2 that I don't like anymore. Actually, maybe we can just undo number 2 completely. I don't think there's a whole lot there that we want. And so we're going to have to kind of do awkward merges, but you know what? That's all right. Struct kanji entry, so and all right. So I just can't let things like this go. Store non-distinct. So we'll get rid of this. Right now we're definitely going to have merge conflicts. Oh, just one file. Okay. So store non-distinct RS. Okay, so what do we want? Which version is closest to what we really need in the end? This is the common parent, I guess. This is code point ordered. Yeah, this is just storing the sort key here. Okay. I guess we want both of these, kind of like a combination of these two. RSC sort key equals C sort key. And we're going to have a new field, kanji I dot distinct RSC sort key equals I. Okay. And the rest is basically all the same. Oh, let's put this. Let's save this. Now we don't want this. It's the totally unchanged version, parent of both. The original ancestor. Commit. Okay. So I copied this part, or what I wanted this, and I did a Q sort, still doing Q sort over here, code point order, but we don't want to actually do this kind of code point ordered. So it's yeah, we don't want that anymore. We just want a code point ordered I equals kanji. Don't need that. So we're gonna change kanji, change that like that, and change the word kanji because we're going to sort the original. Okay, I don't know how this is going to wrap once we finish. Here, let's try this. Okay, distinct. Now we go back to kanji db.h and we add the distinct one. Original index in hard-coded kanji db order. Okay, there we go. Now we can probably get a bunch of failures. Alright, edit kanji db.c 4072. This is okay. We no longer need that. No longer need a dereference. Make. Not enough args. Last rank contained test. Interesting. It's failing. And check kanji database order test also failed. So how is that happening? Kanji db.h. Oh, you know what? I guess I need to do a add all git rebase dash continue. Okay. So now if we go to number 2, it should be fine. 2 is fine. But 1 is what? Returns array in Unicode code point order. Alright. So now we have some kind of a freeze or something. It's caught in an infinite loop somewhere. So make map test, a new sort make map. This does not finish. Okay, edit make map.c. Okay, now where is it not finishing? Now let's see, maybe we can do make clean and then make cc flags equals -g. First key. This gives us debugging information. Now if we do new sort, make map. Okay. gdb mu sort. New sort. Then set args to make map. Run. Okay. Stop. Here. Okay, so we go to kanji-db.c. Oh, it's screwing up here. Why? kanji-db.distinct. Why would it be freezing here? Oh, because it's sorting it over and over again. Sorted equals 1. There we go. That's probably going to fix it. Yes. Make. Okay. So last string contained test is now failing. Probably because we should not be comparing pointers anymore. So let's look and see where we're comparing pointers. Because we want to compare the distinct RSC sort key now, rather than the pointers. So check kanji-db order, and we're going to look for, let's go to line 260, which is, there we go. No, not quite, a little too low. So here, distinct, or dash distinct is less than it, dot distinct. Okay. So I guess what I need to do is I need to be a little bit more patient, because I need to actually look in the commit and see where I didn't. Did I not fix that? Head. Don't on distinct, but so here. So what is the difference between 1 and 2? Why do I have 2 1s here? Okay, 2 has something removed, so we don't want 2 exactly. We want 1 pending. Move it here. Okay. Now. Okay. So key. Okay. So this is fine. That's where we're initializing the database. That should still be fine. And now down here, we have, this is no longer correct, right? We need to go to kanji distribution, then go to line 130 or so. All right. Dash distinct is less than dash distinct. Okay. Next. Another problem line where we're comparing pointers. That's not going to work. Pick cutoff. All right. So key. All right. All right. There we go. Next, any more? Last string contain test. Main.c, that's fine. Util, okay, good. Now, yes, it all passes. Okay, finally. So now this commit is going to be pretty clean because we're just we're really not really changing a whole lot anymore. We're just adding a new sort key, which is distinct, which means every index is different, or every key is different because it's based on the index. Whereas before we just had this, which was the distinct one, but now we have the distinct one renamed as distinct, and one that shares the same radical stroke count key, assuming that the stroke count is the same. Alright. Radical stroke count, 0 stroke count. Resorted. Okay. And we are only using the non-distinct one key. We're only using the non-distinct one in our logic to print the spaces in last string contained, which is where? So here. This is the only time we actually need to use it. So okay, I feel like this now commit is more sane at this point. It took me quite a while to get to the state, and a lot of dead ends and backpedaling, which is unfortunate. I should have been a little bit more well prepared and planned this a little bit more. But here we are, and I don't think we have to review what I did because I already did that when I thought I was going to end the video, but didn't. And but this is the new commit, and it looks like quite simple and self-contained, and I'll be able to explain this easily when I rewrite the commit message here. So thank you for watching. Now here's an addendum. So I had made a mistake before. So we had checked for the flag -c, and if it were true, we just set this to true, show space for cutoff points, and this compared each character against the previous one to see if it had the same radical stroke count key. And the thing is, this was comparing to true very often, and it really rarely grouped things into adjacent characters. And the reason for that was because we were first sorting them by the by the by the ranking rather than the radical stroke count key. And so they're sorted by ranking, and so obviously the characters would change the radical stroke count key from character to character, since they were not sorted by that way in the first place. And so once I automatically set the stroke count line here, let's set. Once I automatically set the sorting to the RSC sort, it actually started to look correct. And last rank contain -c, and so here we have groupings that are actually interesting and show that several characters have the same radical stroke count key. So like here's a pretty big group here, and so these are all hand radicals with 1, 2, 3, 4, 5, 8 residual strokes. Let's check this. 1, 2, 3, 4, 5, 6, 7, 8. Yep, they all have 8. So now we can update this test and commit that. We want to make this. We want to do this in a separate window so that it's easier. Speaking of which, we should add something which shows the copy line for fixing the test, and that would be helpful. So I don't have to do that copy paste so many times. Let's see here. New window, and I'll do copy. There. Okay, so now we can amend it. Oh, yeah, let's do that. So we amend it, and now we can see the much more visually interesting and helpful groupings. So now that we don't have any glaring errors left in the code base, now it would be a good time to stop. So there we go.